working on section 2 of chapter 1, and we're going to be looking, this is kind of our fourth day of being in this section, and we're going to look at the formal definition of limits, being able to identify how close we can get to a limit, and then what requirement we would have of our input, how close we'd have to get to C in order to guarantee a certain output. Two main characters that are going to be used as we work with this formal definition is delta, it's a lowercase delta Greek letter, and epsilon. So this is an interesting diagram, but I think it'll make a little bit of sense. The limit of a function is the height. We've talked about that. It's the y value that we would expect when we get close to a particular x value. So the closer I get to my x value, the more accurate I am at exactly my C value, my target value. But I will be off a little bit, and that means then my output, my y value here, will be somewhat different than the targeted limit. So what the question is, if I want to be within a certain range of my limit, this range in between here, how close must I be then when I put in an input value? How close to C do I require myself to be in order to guarantee a certain output? And that's it's very abstract idea to wrap your head around. So I've got this Desmos example that we could go to, and this is of course working with just a quadratic function, and I set my C value to be 2. You can see my C right here at 2. So my limit as x approaches 2 of the function x squared is equal to something. Well, we know it should be 4, right? As I come into 2, exactly at 2, I'd be 4. But now we're really talking about in the area near 2. And so what I would say is, if I have a certain amount of accuracy I want of my output, this would be my epsilon. So I could be 4 plus epsilon, and that would give me this higher output range. Or I could be 4 minus epsilon, and that would give me my lower output range there. So where would I have to be as far as an x value in order to get that? Well, to get in that range, then my x has to be a certain distance away from C, and this is what we call our delta value. How large can delta be in order to ensure that I'm within this epsilon range or in the purple zone? And we can adjust this a little bit. Oops, I really messed that up. If I adjust this in a little bit, and I can't, my sliders are not working here, guys. Let me go back up. There they are. All right. There's delta. So you can see I can make delta really wide, but then look at my output. My output range says I'm going to be from down there to possibly up at 8, so below 2 and almost up to 8. I don't want that big a range, so I need to tighten my delta so that my range isn't so wide. And ooh, there's a good spot. Actually, I have to be pretty darn close to 2 there, don't I, in order to expect an output of epsilon either plus or minus epsilon from 4. So this is what we're after. We're trying to figure out, what should delta be? How close to C do I need to be? All right, so back to our presentation here, and let's just do some examples. So this is the very formal definition of a limit. Let f be a function defined on an open interval containing C, except possibly at C, and let L be the real number, and here is let L be a real number. The statement then says the limit as x approaches C, some target value for x, of the function f of x will be equal to L, our limit. This means that for each epsilon greater than 0, there exists a delta greater than 0, such that if the absolute value of x minus c is less than delta, then I know that f of x will be f of x minus L, absolute value, the result, will be less than epsilon. And it is kind of this picture here that we have showing in the shading. You know, here's my L value, and then this would be L plus epsilon, L minus epsilon. If I want to be within that range, then that's going to require that here's my C, that I am within C plus delta to the right, or take off delta to the left, and I can have my left boundary and my right boundary, and I would need to select some C value, C sub 1 value in that zone in order to guarantee an output in that zone. You may want to draw that picture in your notes. Just hit pause. So let's do a problem. Given the limit as x approaches 3 of the function 2x minus 1, and I don't have the limit provided there, do I? Because we're going to calculate that. We can. And then it says find the delta such that the absolute value of 2x minus 1 minus 5 is less than 1/100th. Whenever x minus 3, absolute value, the difference, is less than delta. Well, this is a lot going on, but really what I'm coming back to is this formal definition of the limit. And we actually start at the end and look at our output first, and then that will give us an indication for our input, how close our x value must be to c. This is my function, isn't it? Right there, I can pick up the function, that's f of x. This is my c value as x gets close to c, or x gets close to 3. The limit on this, I can simply substitute 3 into this and get it. So step number 1, let's calculate out our limit. Calculate the limit. And I can calculate that limit by simply going 2 times 3 minus 1. It's a linear function. So as I put in 3, I would get out 5. So that tells me my limit L value is 5. And if you want, you can go up there and plug that in. So this becomes L. Now what we want to do is set up our epsilon statement. And that statement is really driven off the definition of a limit. And I'm coming right on this one. So we take the absolute value of the function minus the limit, has to be less than epsilon. Our function was up here, 2x minus 1. Our limit is 5, and we want it to be within 1/100th of a unit. Our goal is to find out about the absolute value of x minus 3. And you're going to like this. So now our goal, sorry this went blank, our goal is to find delta. And that delta is driven by x being a certain distance away from c. And our c value was 3, the limit as x approached 3. So here's what I need to do. I need to make this look like absolute value of x minus 3. If I can do that algebraically, I can figure out delta. So this will be pretty easy, won't it? So here's we're on step 3 here for solving this. 2x minus 1 minus 5 less than 0.01 is like saying 2x minus 6, isn't it? Just simplifying -1 with -5. Notice how they have a 2 in common, so let's factor out a 2. So we GCF that 2, and I have 2 times absolute value, or absolute value of 2 times x minus 3. If I could pull out the 2, I would have absolute value of x minus 3, and that's a match. And we can bring the 2 out front, and I'll bring it out as a positive 2, since it would have been absolute valued, and it was 2 anyway. It's almost the same. Divide both sides by 2 now, and it's like magical here, isn't it? This is exactly what we were after. I get the absolute value of x minus 3 being less than 0.005. And this statement is a nice match to this statement up here. So that means then that absolute value of x minus 3 is less than delta. That delta has to be 0.005. And that was our goal, was to find delta. Let's try another. Assuming the limit as x approaches 1 of the function 6x plus 4 is equal to some limit, and that epsilon has to be 1/1000th of a unit away from that limit, please find delta to make that happen. What delta would give us an epsilon, a guaranteed epsilon of 0.001? Well, first off, let's find our limit. And on this one, we can use substitution to do that. So the limit as x approaches 1 of 6x plus 4 will turn out to be 6 times 1 plus 4, or 10. So this is my L value, 10. This is my C value, because I'm going to need that. And this is my f of x, isn't it? So a couple key things to keep in mind here. We got an f of x, we got a c value, and we have the limit, all of which are needed to create the definition of the limit. So step 2, let's write the epsilon statement. We actually, you can see, kind of start with what we want to have as an outcome, and then that'll lead us to what we need for an input. Write the epsilon statement. Okay, so absolute value of the function minus the limit has to be less than epsilon, which they defined up here as, we want to be really very, very close, 0.001. Then what we want to do, we want to have this match up to our delta statement. And our delta statement is 0 is less than the absolute value of x minus c, and our c is 1. We were approaching 1 is less than delta. So I know what my goal is. I want to get the absolute value of x minus 1 and transform my epsilon statement so that it matches that requirement for my delta statement. So let's just take and go 6x minus, this would be negative 6. 6x minus 6 will be less than 0.001. Factor out a 6 from this. Divide, well, we can move the 6 out front as a positive 6. And then we will divide by 6. And I don't have a calculator with me right now, so I'm going to just pause this for a moment and get it. All right, that turns out then that absolute value of x minus 1 is less than I do not have a correct answer there. Okay, there we go. It's 0.00016. And that means then that my delta would be 0.00016 repeating. We have to be really, really close to C in order to guarantee that our output will be within 1/1000th unit from L. Last one, and then we'll call it a day. So part C, assuming the limit as x approaches 2 of 3x minus 2, what delta would be chosen for any given epsilon? Notice this time they're not saying that epsilon should be within like 0.01 or anything like that. They're just saying given some value for epsilon, what would delta have to be? So the same thing here. Let's find our limit. The limit does exist for this, so the limit as x goes to 2 of 3x minus 2 is equal to plug in, or substitute's a better word, substitute 2 in for x and we get 12 minus 2 is 10. My L value is 10, my C value is 2, my function is 3x minus 2. And with those things identified, I can write my epsilon statement that f of x minus L is less than epsilon. My f of x is 3x minus 2. My L is 10, which is the limit, is less than epsilon. That makes 3x minus 12 less than epsilon. And notice I can factor a 3 out. So I'm going to go ahead and do that. And that would give me absolute value of x minus 4 less than epsilon divided by 3. Okay, I kind of just got on a roll there and kept calculating. What is the delta I'm after? Well, the delta I'm after is x minus c, correct? And in our case, our c value, we were a limit that was approaching as x approaches 2, so we'll have x minus 2 in here has to be less than delta. Did I goof up somewhere? Ha! Way back, didn't I? Where did I come up with 6 here, people? 3. 3 minus 2 gives me 4. 4 goes in here, and 4, that gives me negative 6. This creates a 2 then factoring out, and that makes 2. Sorry for not catching that sooner. There's some numbers that you're going to want to update, guys. All right, because now we have a nice matchup, don't we? I knew something had gone wrong because I wasn't getting the match that I really wanted to. Otherwise, I was going to have a lot of work to do. So since the statement is equal, then this means that our delta would have to be less than epsilon divided by 3. There is that's enough for today, and then we'll pick up on the next day 2 of this section. There is no homework following this one right now. So see you the next lecture.